In this work, we investigate the dynamics of a wave packet in phase space using initial value representations, and we put a particular emphasis on how this wave packet interacts with an external field, which is either static or time-dependent, and a binding potential. And the reason why we are analyzing this is because in my field, which is strong field and attosecond physics, trajectories are paramount. And these initial value representations, they describe the wave packet by a swarm of Gaussians which are guided by trajectories. People have been using a lot of trajectory-based methods, but sometimes you gain on one side and then you lose on the other side. Either you do it classically and then you don't have tunneling or quantum interference, or you do it quantum mechanically, but then you have to make radical approximations upon the potential, which means you are losing a lot of information, especially because nowadays we are starting to look at more complex systems like big molecules, like nanostructures. So we need methods that treat the field and the potential on the same footing. We had an unusual situation because we were starting from a state which was initially bound. And this is not what people normally do in these fields. They consider that the wave packet is starting from far away. So we had to understand if we could use these methods under such circumstances and make a detailed analysis of the ionization dynamics. What we had to do is we had really to look at the phase space and determine the regions which would correspond to bound motion, unbound motion, and in this context then try to see what was happening. So we had to generate an initial swarm based on an initial wave packet, and the first thing we have realized is that this swarm of trajectories occupied several phase space regions which were either bound or unbound. Then we looked at a way of establishing the correlation between momentum and position, and we picked up a quasi-probability distribution which is used in quantum optics, which is the Wigner quasi-probability distribution, and we started to analyze how it forms, both for the initial value representations we were using and using as a benchmark a Schrödinger solver. So what we have realized is that there was a tail which was forming, and this tail was going from the bound phase space region to the unbound phase space region. And it was moving in a way that it was suggesting that the electron was reaching the continuum with an energy higher than that necessary to overcome the saddle, which was determined by the joint action of the potential and the field. But as time went by, we realized that this tail started to move towards lower momenta, and that wasn't very clear to us why this was happening, because this would imply that a classically forbidden region was being crossed. And these trajectories here we are using, they are classical. So what we did then was, let's eliminate the trajectories which form this tail and look at them. And these trajectories, they were not crossing any separatrix. They were obeying all possible classical constraints. But what was happening was that if they are removed, the tail disappeared. We decided to pick up a method which is better. It's another initial value representation, but instead of using the classical Hamiltonian, we used a quantum mechanical averaging of a Hamiltonian which would introduce corrections. And the agreement got better. And we realized that in this case, these trajectories defined by this other Hamiltonian, they were crossing the separatrix because of these corrections. So we had these two methods and we had a benchmark, and we had to test these against a phenomenon which occurs in strong fields like harmonic generation, because it's a coherent phenomenon. So if you have phases of the wave function, it's going to be picked up, and it occurs close to the core. So we decided to check, and we found, in fact, a very good agreement, not perfect, but very good, between the Hermann-Klug propagator and the full solution of the time-dependent Schrödinger equation, including the maximum harmonic energy and interference substructure.